Hi everybody. So last time we talked about reflection of light. So if I do a small recapitulations, we have done laws of reflections, and we talk about important parameter involved in reflections such as focal length, focus, radius of curvatures, image, types of image, and then we talk about image formations, and finally we talk about mirror equations. And this equation help us to find the image formations, without drawing array diagrams. And this equation is valid for any type of mirror, including concave mirror as well as convex mirrors. And this equation can be valid for even plane mirror. So today what I'm going to do is refraction, the second topic of this chapter, refraction. Let me start something like this. What do you mean by refractions? Alright? And where refraction taking place? So let's say I have two transparent mediums. Let's say two transparent medium. If I draw, let's say I have a glass slab, and when a light travels obliquely, alright, when a light travels obliquely from one medium to another medium. This is medium number 1, this is medium number 2. When a light travels obliquely from one medium to another medium, alright, two things will take place. First, we have done in reflections, some part of light undergo reflection, and the remaining part of light undergo what we call as refractions. This is what we call as a bending of light. Alright. So when a light travels obliquely from one medium to another medium, alright, two transparent media, right? Then light undergo a bending of light. You find a bending of light at interface surface. This is called interface surface. Alright. And the bending takes place at the interface surface, and this bending is what we call as refraction of light. And now let me tell you why we have to write obliquely. If a light travels normal to the mediums, no refraction will take place. You have learned this in lower class. No refraction will take place. The light undergo refraction only when light travels obliquely from one medium to another medium. Alright. So there is a bending of light taking place, and this phenomenon is what we call as refraction of light. So like reflection of light, in case of refractions, it has again two laws. So all the refractions taking place has to undergo two laws, right? So first law, very similar to, let's say, laws of reflection. This is incident light, alright, and I'm going to draw a normal, and this is angle of incidence, and a refraction take place. Bending will take place. Alright, bending will take place. Let's say this is medium number 1, this is medium number 2. first medium and second medium. And let's say this angle is what we call as angle of refraction. This angle is what this is called refracted ray. This is incident ray. The first law says that the incident ray, refracted ray, and the normal line, let's say normal line to the interface surface, to the interface at the point of incidence, all lie on same plane. This is same as in case of reflections. This is incident ray, refracted ray, normal line should lie on the same planes. Alright. So this is our first law. And the second law talks about angle of incidence and angle of refractions. The second law says that the ratio of angle of incidence, ratio of side of angle of incidence, ratio of side of an angle of incidence to that of sine of angle of refraction is always constant. Always constant. And again, very important point you have to keep in mind is this is a constant for given pair of media and for given wavelength of light. This tells that this constant varies from pair of media. That means if I change the two mediums, constant will change. And this constant also depends on a wavelength of light. If I use a red light, it is going to change. If I use a yellow light, it is going to change. So therefore, the constant depends on medium and wavelength of light. Right? If I choose a particular pair of media and a particular wavelength of light, only then this remain constant. This remain constant. And we say that the constant is what we call as, this constant is what we call as refractive index. Refractive index. Refractive index of a pair of media. Refractive index of pair of media. This is what we call. And this is what we call as, let's say, n to 1. So this is what we call as refractive index. Alright, refractive index of second medium with respect to first medium. So I have mentioned this second medium with respect to first medium. So that means this constant depends on two media. Alright, so this is what I have done. This is constant. N to 1. So therefore, I would like to write here sine I divided by sine R is equal to n to 1. Alright. And again I say that this refractive index is, this constant is also defined as the ratio of velocity of light in the first mediums divided by second medium. The ratio of velocity of light in first medium to that of second medium. This is again what we have, a relations. Alright. This is n to 1 is equal to V1 divided by V2. Alright. And then I do a small simplifications. So let's say I have N21. Okay, let's say I have C. Let's say I have C. What is C is what we call as velocity of light in vacuums. Velocity of light in vacuums. All right. If I choose first medium as a vacuums, then I will write this as N21 is equal to, what is that? V1 divided by, this is what we call as N2, and then divided by N1. So N2 is a refractive index of a second medium with respect to vacuum, and 1 is refractive index of a first medium with respect to vacuums. Again, this is what we have, and this is what we call as absolute refractive index. Absolute refractive index. This is what we call as absolute refractive index. Why? So this determines the refractive index of only second mediums. Again, N1 is also absolute refractive index of medium 1. N2 is absolute refractive index of medium 2. Alright. So having this, I can write again here. I'll write this. Sin I divided by sin R is equal to N21 is given by N2 divided by N1. Alright, and equation equal to N2 sin R. This is simple equations, and this equation is what we call as Snell's law. Snell's law. So we have, this is refractive index of a first medium, and this is a refractive index of second medium. I is angle of incidence and R is angle of refraction. So this is what we call as Snell's law. Alright, so we can relate refractive index with velocity of light. Alright, and then we can relate the refractive index with its absolute refractive index. Alright, so now I would like to define here denser medium and rarer mediums. Alright, so if N, let's say N2 is more than N1, alright, so the medium 1 is more than, if N2 is more than N1, medium 2 is denser than medium 1. If N2 is less than M1, then medium 2 is rarer, this is R, rarer than medium 1, right? Medium 1. Alright, so again, velocity of light, if a medium 2 is denser than medium 1, velocity of light in a second medium is less than velocity of light in a first medium. If a medium 2 is rarer than medium 1, then the velocity of light in a medium 2 is more than velocity of light in medium 1. Alright, so this is how you read it. So therefore, we call it as an optical denser, we call it as an optical rarer. Alright, so this is what we have. Therefore, I would like to have a small conclusions that if a light goes from denser to rarer, this is the case. If a light goes from, let's say, if a light goes from denser to later, then I will define how bending takes place. If a light goes from denser to rarer, let's say light goes from denser to radius, alright, and the bending is away from normal, If a light goes from rarer to denser, this is an example of rarer to denser, right? If a light goes from rarer to denser, then bending is towards normal. Bending is toward normal. Alright? So here in this case, since the bending is away from normals, angle of incidence becomes less than angle of reflection. Here in this case, since the bending is towards normal, angle of incidence becomes more than angle of refraction. So these are the things that normally take place in case of refraction of light. So absolute refractive index and how bending takes place away from normal towards normal. This is all defined by the two media. Now if I take a 3 media, let's say I have a small problem, right? I have a 3 media, alright? Medium number 3, medium number 2, and medium number 1. So it is said that N31 is given and N21 is given, and you are asked to find what is N32. Alright, so N31 is given, N21 is given, and how to find out N32? So let's say light travels from one medium to another medium and then next medium, and you are asked to find what is the refractive index of third medium with respect to second medium. Alright, so this is very simple to define. Let's say I have this. This is defined as N3 divided by N2. Alright. And then what I do is N32 is equal to N3 divided by N2 multiplied by N1, N1. Small algebra. Alright. And then what I do is N3 divided by N1 multiplied by N1 divided by N2. Okay. So after simplifying, let's say N32 is equal to, what is N3 divided by N1? Refractive index of third medium with respect to first mediums. Multiplied, what is the refractive index? What is N1 divided by N2? Refractive index of first medium with respect to second mediums. Alright. Alright. And then I just put here not. N21 is equal to N12. These two are reciprocal. Alright. So therefore, N12 is equal to N21. Alright. So this is what we have. This is the answer. So, since this is given, this can be found, and 3-2 can be found. Alright, this is how we do, right? Now next what I'm going to do is refraction through some transparent medium. We will discuss how refraction takes place through a rectangular prism, a rectangular glass tab, and how refraction takes place through glass of water, and how refraction takes place through atmosphere. So I have here rectangular glass slab. Alright. So I have incident light. This is the incident light, and you see refraction taking place. Otherwise, light has to travel like this. Let's say light has to travel like this. If no refraction takes place, then light has to travel like this. However, since this is air mediums and this is a glass medium, alright, so the refractive index are different. Therefore, light undergo a bending. And we have to draw a normal line. Let's say I have a normal line. Okay, so this is angle of incident. Angle of incident always between incident ray and normal line. This is angle of refractions, incidence. If I say I draw this line ray, if no refraction takes place, since this is the glass, it undergo refractions. So therefore, the bending takes place. Instead of light traveling through this path, light to this path. So this bending is what we call as refraction of light. Now let us do this. I have a glass slab here. Alright. Incident light. Alright. This is angle of incidence. Then this is air medium. And now bending is towards normal. Alright, this is glass mediums. And since the air is a radar compared to glass, bending is towards normal. This is bending towards normal. Bending towards normal. Now here, light goes from denser to rarer, bending is away from normal. Alright, this is bending away from normal, this is bending towards normal, bending away from normal. Alright, so I just extend this incident ray. I extend this incident ray. Now I say if I let the incident ray go without refraction, this is the path which I have told you. Now you see here in case of glass slab, rectangular glass slab, angle of incidence is always equal to angle of refraction, angle of emergence. This is angle of emergence, this is angle of incident, this is angle of refractions. So when a light comes out from a glass slab, this angle is equal to angle of incidence. Alright. Therefore, incident ray and emerging rays are parallel. These two are parallels. And this distance is what we call as lateral displacement. This is done in class 10. This is called lateral displacement. Alright? So angle of incident is equal to angle of emergence. And if you ask why angle of incident is equal to angle of emergence, the reason is simple. Since this surface is a plane and the emergent surface is a plane, this case bending is towards normal, and whatever bend towards normal is being compensated by the bend away from normal. So therefore, what is the net bending? Zero. I say if this is bending toward this side, this bends toward that side. So therefore, they cancel each other. Hence, I must be equal to E, and this is what we call as lateral displacement. Alright. Lateral displacement. It is done in class 10, like what are the factors that affects lateral displacements? This is determined by angle of incidence. This is just a recapitulation of class 10, and it is also determined by thickness of mediums. All right, angle of incidence, number 1, and number 2, thickness of medium, number 3, refractive index. So these are the 3 factors which determine lateral displacement. All right. Now this is for glass slab. Next, we will have another effect of refraction. This is again done in a lower class. If I put pencils or anything stick inside a glass of water, you see some changes. The thickness of pencil will change, become a little thicker, and when you look at the interface surface, there is some kind of shift. Alright, and this is all because of refractions. Alright, maybe you can draw a ray diagram and get your result, right? So this is done in a lower class. And then this is due to again refractions. Again we have this. Another effect of refraction is when we go and visit swimming pools and all, we see the changes in the depth of swimming pool. All right. So when you see in any angle, all right. So you see you find some two different depth. One is what we call as actual depth. Another one is what we call as apparent depth. So why there is an apparent depth? Why the floor, right, ground floor of a swimming pool is little upward, right? Why? It is all again because of refraction of light. All right. So this is what this is done in the ray diagram. So this is the actual depth, and when you see through glass, through water, refraction takes place. Light has to come from the floor of swimming pool. Let's say this is the point on a swimming pool, and light undergoing a refractions. So this is the bending away from normals. Let's say I can do this. This is a normal line. Let's say this is normal lines. Bending is away from normals. Let's say this is the normal lines. Bending is away from normals. So since bending is away from normals, how the image forms? I have to extend reflected light, reflected ray, and reflected ray merge at this point, and this is considered as apparent flow, and this distance is what we call as apparent depth. Likewise, when you see swimming pool obliquely or with some angle, obliquely means with some angles, again you see there is a rise of a flow, rise of what we call a flow, right? This is what. So therefore we have, this is the apparent depth, this is the apparent depth, and this is the real depth. All right, and therefore we say that this again, the height of the apparent depth is again determined by refractive index. Apparent depth is determined by refractive index. All right. So this is one point. Another effect which we are going to discuss is sun rises earlier and sun normally set little delay, and we say this is of 2 minutes earlier and 2 minutes later. Alright, so why there is delay and advance of sunrise and sunset? Advance sunset and delay sunset. Why? Again, reason is atmospheric refractions. Again, we can explain this. When a light comes from a sun and enter through this atmosphere, the density, atmospheric density varies. Alright. So it becomes denser and denser, and then you see a curve. Alright. And when you actually see, you are here. Alright. And you feel that light comes from a sun, appearance sun. This is appearance sun. This is what we call appearance suns. And this is what we call actual sun. Alright. One is called appearance sun, other one is called, why? Again, atmospheric refractions. Why? Again, we call it as a atmospheric refraction. There is apparent change in a position of sun. Alright. Likewise, this is what we call as a horizons. No, if actual sun is below horizon, we won't be able to see. Why? Because light doesn't go in a band, right? However, because of atmosphere bending take place, therefore sun appear earlier. Alright. Likewise, we can define delay in sunrise, sunset, and advance in sunrise. Okay. Now we'll talk about total internal reflections. Alright. Before I discuss the total internal reflections, let's say I have water. This is water, and this is air. First we will define what is internal reflections. What is internal reflections? Normally we say that when a light goes through a transparent medium, it normally passes through one medium to another medium. But we say that if I send a light like this, I told you some portion of light undergo reflections away from normal. Some portion of light undergo reflections. So reflection taking place in the same medium. Alright? Reflection taking place in the same transparent medium is what we call as internal reflections. Reflection taking place in the same transparent medium is what we call as internal reflection. I didn't discuss total, right? So internal reflections, right? So this is what we have. When a light, let's say this is let's say a denser medium. This is denser mediums, and this is rarer mediums. And when the light goes from one medium to another medium, two things will take place. One is refractions, other one is reflections. Even we discussed this in a previous topic also, right? So this reflection is what we call as internal reflections. So reflection is taking internally. Alright. And now what about total internal reflections? Alright. So let's say I say when a light goes from, let's say again I'm going to write, when a light goes from denser to rarer. When a light goes from denser to rarer, bending is what? Bending is away from normal. Bending is away from normal. So when I say a bending is away from normals, then I take this. This is interface surface. Let's say this is interface surface. Interface surface is a surface which divides two media. Right? This is something like a border between two media. Right? And this is denser mediums. Let's say water mediums. I write here denser mediums. Denser mediums. I say refractive index is 2, and is rarer medium. Let's say refractive index is N1. So the bending is away from normal, right? So I just say this light, some angle of incidence. Let's say I told you this undergo refractions away from normal, and some light undergo reflection also. All right. Now again, if I go on increasing, look at here, right? If I go on increasing, if I goes on increasing, then R is going to increase. And we see that every time I is less than R. Why? Because the bending is away from normal. Alright? As I goes on increasing, R has to increase. However, there is a limit to R. Alright? You can go on increasing R, alright, till the interface surface. You can't increase R beyond interface surface. So this is the trick, right? So therefore, again I am going to set a light with little greater angle of incidence. Then you see refraction with, let's say this angle of incidence is what we call as I prime, angle of refraction is I R primes. So R prime is more than R. Now I say, again I set a light with angle incident more than I prime. Let's say this is, I say I double prime. I double primes. Alright. So then you will find. So I told you just now that the limit of angle of refraction is only along interface surface. So I increases. Now this is the reflected light pass along interface surface. So this angle is a 90 degree. So therefore the maximum angle of refraction can be maximum angle of refractions can be 90 degree. Alright. And I say this angle of incidence is what we call as critical angle. This is what we call as critical angle. Alright. And now if I increase angle of incidence beyond critical angle, right, I am going to send a light, and this light goes like this and falls on interface surface. Now here no refraction is taking place. No refraction is taking place. There is only reflection taking place. So this is, let's say, I'll use blue pen. I triple prime, which is equal to R triple prime. These two are equal. Alright. This is what we call as total internal reflections. It is more than internal reflections. Whatever light you send is undergoing internal reflection. So this is what we call as total internal reflections. Here also reflection is taking place. This is again, there is a reflection but not total internal reflections. There is a reflection but not total. This is the reflection, right? This is the reflections where you find, alright, 100% reflections. So this is what we define as total internal reflections. This is what we define as total internal reflections. So therefore we have one very important concept, what we call as critical angles. Critical angle. Alright? So what is that? Angle of incidence is IC. This is what we call as critical angle. So we define critical angle in one very simple way. Critical angle is an angle of incidence at which angle of refraction is equal to 90 degrees. So I just say, I define it now. Very simple, say angle of incidence is equal to critical angle if and only if R is equal to 90 degree. R is equal to 90 degree. R is angle of refractions. So critical angle, if angle of incidence is equal to critical angle, the condition satisfied should be that angle of refraction must be 90 degree. So this is the point. Now look at here, the condition for internal reflection to occur is that first light has to go from, first condition is that, I just write here condition, two important conditions to satisfy total internal reflection is, first is that light has to go from denser to rarer. Light has to go from denser to rarer. Second condition is that angle of incidence must be more than angle of a critical angle. These are the two conditions should satisfy total internal reflection to take place. Light should go from denser to rarer mediums. And what is the advantage? Then there is the bending is away from normals. Advantage is that angle of incidence is less than angle of reflections. Then second is angle of incidence should be more than angle of a critical angle. So these are the two conditions. And one of the most interesting thing about total internal reflection is we find so many natural phenomena, right, which occurs because of total internal reflections. So the interesting thing about total internal reflection is in nature we find so many phenomena which occurs because of total internal reflections. Again I am repeating. In nature, we find so many phenomena, so many illusions, alright, which occurs because of total internal reflection. So, and it has also a huge technological application. So, we'll discuss few of. Look at here, and now before that I would like to have a refractive index of a few different medium. So water having a refractive index 1.33 and critical angle of the water is going to be 48.75. A chrome glass refractive index is 1.52. Critical angle is 41.14. Dense flint glass refractive index is 1.62. Then critical angle is 37.31. And diamond having highest refractive index, that is 2.42 and having a smallest critical angle. Now when you look at this data, we find that there is some relationship between critical angle and refractive index. So we will find out before we do some phenomena related to total internal reflections. We will find a relation between refractive index refractive index and critical angle. Refractive index and a critical angle. Let's say I have a Snell's law. This is a Snell's law, and a light goes from second medium to first medium. This is how we define. Why? Because the second medium is a denser medium. First medium is a medium 1 is a low. I will say this is a medium 1. This is medium 2, and the light goes from medium 2 to medium 1. Why? Because medium 2 is denser than medium 1. So this is the first condition we have to satisfy it. So condition number 1 is done since light goes from denser to rarer, and 2 is a denser medium and 1 is a rarer medium, and this is how we get this Snell's law. Then apply this for I equal to IC. If I is equal to IC, then we have R must be equal to 90 degree. I'm sorry, this has to be 1 2. Why? Because light goes from second medium 2 to medium 1. That is why I put 1 2. Alright, again I'm repeating, since light goes from medium 2 to medium 1, therefore it is an 1 2. Why? Because for total internal reflection to satisfy, light has to go from denser medium to rarer mediums. Light has to come from denser, then goes into rarer medium. That you should keep in mind. And then second condition is that, this is the first condition, I should be equal to IC, then R is equal to 90 degree. So therefore I just write here IC, then sine 90 degree, and this is equal to 2. Alright, this is the refractive index of medium 1. I'll write here refractive index, don't confuse. Alright, refractive index of medium 1. I'm not saying first medium, medium 1 with respect to medium 2. Alright, and then I say sine 90 is 1, sine IC is equal to n1 2, and we have already derived that n1 2 is equal to 1 by n2 1. Alright, so therefore sine IC is equal to 1 by n2 1. Alright, and n2 1 is equal to 1 by sine IC. Yes, this is the relation. This is the relation between refractive index and critical angle. So because of these relations, we found that as a refractive index increases, critical angle has to decrease. So the diamond having a highest refractive index and having a least critical angle. So this is how we define it. And this is frequently come in exam, right? The relation between refractive index and critical angle. Right? So that means this and critical angle also defines a property. No doubt this is going to be a property of transparent mediums, and this is also a property of transparent medium, right? So now we would like to discuss phenomenon related to total internal reflections. Alright, just now I have mentioned that in nature you find so many illusions, all because of total internal reflections. In nature we find so many phenomena that can be explained by a concept called total internal reflections. Alright, I will discuss first is mirage. Alright, Maybe you have done this in the lower class also. You might have learned this in different. Maybe you might have come across this topic in a storybook also, something called a mirage. And might be you might have come across this phenomenon, right? So what is that mirage? All right, mirage is optical illusions. Mirage is an optical illusion, and this is an optical phenomenon or optical illusions which occurs because of total internal reflections. What kind of optical illusion it is? All right, during a very hot summer times, all right, especially in a desert area, you find appearing water. You see a water, but you won't be able to get water. Why? Because of mirage, right? So we'll discuss formation of mirage, right? Formation of mirage. This is explained, right? So during a very hot summer times, ground gets heated up, all right? Air density around ground or at ground is less. Why? Because heating takes place. And then because air density at the ground is less, refractive index is less. So now you find the changes of refractive index all along the layer of atmosphere, all right, about ground. So as you go down towards ground, refractive index start decreasing. All right, that means light start traveling now from denser to rarer, right? So now in case of a hot summer times, all right, instead of light traveling straight, light travels like a bending. Why? Because every moment light undergo bending. And that too, what kind of bending? Away from, you see, bending is away from normal. Bending is away from normals. Alright? And it bends away from normals such that at certain point it satisfied total internal reflections. When a light incidence near ground such that the angle of incidence is more than a critical angle, then instead of light just falling on the ground, it undergo total internal reflection. Alright? Total internal reflection. So therefore, this is observed, and you see that observer feels that light has come from the ground. Light has come, there is some kind of reflection from ground. And normally say the reflections are taking place reflections are normally occurs due to water. So therefore, you see some kind of reflection from certain distance. Alright. So therefore, we find a mirage. You see, there is full of waters, alright, far away from you. So this is what we call as mirage. So one very important thing you should keep in mind in case of mirage is it should be during a very hot summer times, because of which air density vary. Alright, air density remain thinnest at a ground, just about ground, and as the light goes from higher to lower, refractive index keeps on changing, so it keeps on bending. If the angle of incidence near ground is more than critical angle, then it undergo total internal reflection. This thing you should keep in mind. So I have few more. This is again diagram. So if you see directly, you can see trees, but then because of a hot summer, right? Instead of this light goes straight, it undergo a total internal reflection. And this person feels that there is a water near these trees, therefore reflection of a tree is taking place because of water. So this is what we have in case of mirage. Alright? And again, this is textbook diagram, and here no mirage formation take place. This is normal conditions. This is normal conditions where there is no mirage formation take place. So therefore light travels straight. Why? Because the air density remain almost uniform all along atmospheres, right? All along atmosphere, right? So therefore light travels straight. Alright, so here at a uniform temperature, a constant refractive index, and the air density also remain constant. So you can write here air density remain constant, then the refractive index remain constant, the temperature remain uniform all along atmosphere, and no reflection take place. No total internal reflection take place. You see trees. And then now during a hot summer times, alright, instead of light, this light, again I am explaining, right, repeating, right, instead of light going like this, light undergoing total internal reflections. So this is a warmer air at the ground, near ground, having a less refractive index, and this is little cooler, more refractive index, alright, less warmer region, and light undergoing a continuous bending, and this person feels that there is a reflection of a tree taking place at the ground, alright, which is all because of water. So therefore the person sees that there is a water at a distance, alright. So, but which is not true, this is all because of total internal reflection. And then one thing you should keep in mind is you need a few conditions to satisfy mirage to take place, or mirage to formation of mirage to take. Alright. So one thing is that the distance, right? One thing is that the temperature difference should be a little high. Another point is that the distance, alright, distance should be a little far apart, alright. Therefore you see that the apparent water goes away from you, alright. You won't be able to reach nearer to the apparent water. Why? Because the distance is fixed, alright. If distance is fixed, so therefore you see that maybe if you reach this point, your apparent water may move to this side. So therefore, something like water goes away. Alright? This is illusion, and that deceives even a desert animal. Right? Animal goes on and seeking for waters, and animal sees waters at a distance, but couldn't get that water. Why? Because it is mirage. This is the first optical phenomenon because of total internal reflections. Second I have is again the diamonds, right? When I say diamonds, this is a precious stones, and if I ask what is the special characteristic of diamonds, I'm sure people will answer, alright, diamond sparkles when the light incidents on the diamonds. Diamond sparkles. You see a shining of a diamond when a light incident on a diamonds. And maybe you find another glass ball which sparkle less. Alright. Diamond shows maximum property. Therefore, diamond is normally used for ornamental purpose. Right. So now the question is, why there is a maximum shining, or why diamond sparkles when a light incidents on diamonds? If I ask you a question, why diamond sparkles when a light incident on a diamond? Again, reason is that, alright, the diamond, just now we discussed that diamond has maximum refractive index. Diamond has maximum refractive index. Alright, therefore it has a least critical angle. Alright, and therefore, again I'm going to bring here, therefore, alright, maximum total internal reflection take place. Maximum total internal reflection take place. So therefore, diamond shows this property. Just now we discussed that diamond having a refractive index something like 2 point something, whose critical angle is something like 24 something. So therefore, the 75% of light undergoing total internal reflections, right? So therefore, I'll show you a few diagrams. This is the diamonds, and again you can hear. If you put a design on a diamond, then there is greater shining. Why? Because there will be a greater total internal reflections. All right. So this is a diamond. All right. And when a light, this is a light falling on a diamonds, and you see a light undergoing total internal reflection. Instead of light going out from a diamond, it undergoing a total internal reflections. So therefore, you see a shining or what we call a spectacular brilliance diamonds, right? So another diagram I have here. This is again, this is an incident, this is reflection. So you put different design, all right? This is all about diamond. Now the next I would like to discuss is of prism, all right? Next I'm going to give example of a prism. This is a special, prism. This is what we call as a right triangular prism. All right. This is a right triangular prisms. So you will be having the bending of light. This is the 90-degree bending of light taking place. This is 180-degree bending of light take place. And look at here. This is an object. I'm not going to draw diagram here. This is an object. AB is an object, and light from B and incident on this. This is angle is 45 degree. What is the critical angle of glass? Much less than 45 degree. So instead of light going out, you see a light undergoing total internal reflections. Light undergoing total internal reflections. So since the light comes normal to the surface, no reflection take place. You see this is the image of B. And the light from A goes to this, same angle is angle of incident is going to be a 45. Again you see this is the image of B. So now look at here. The image there, if you put some candle or whatever, pin, whatever, right? And if you see candle through this. If I extend this, you will see something like this. BA, like this. BA. So therefore, it is going to be inverted. Same size, inverted. This is what you are going to see. You can perform this activity in a class also when you return, right? And again, we have this is again a prisms. This is 90 degree again. So I allow this is again a B. I allow light to pass through this. Again, this is 45 degree, undergoing again a total internal reflections. Again 45 degree. This is the image. Same, I say this is the point B, point A, undergoing a total, this one total internal reflection, this two total internal reflection take place. Alright, so this is the image. So therefore you say, when you see from this side, this is I, if you see from this side, you will see object like this. Alright, so this is going to be again inverted. This is going to be again inverted. This is apparent, right? So this is for glass prism. One more I have. This is the glass prisms. Again, you do it. Here again you have one total internal reflection take place. Now I think you don't need much explanation. Alright, same. Alright, and then when you see from this side, you will see inverted image. Alright, image is going to be inverted. So if I put eye here, you could see object. Alright, which is inverted. This is going to be image. Alright, these are the different images formed because of total internal reflections when you pass through. What is that? When you allow a light to pass through prism. Now I have a last phenomenon, which is what we call as technological application of total internal reflection. Technological applications. So this is what we call as optical fiber. This is what we call as optical fiber. So there is now a big branch of physics called optical fiber, right? Physics, right? So this deals with a light or information traveling through optical fibers, right? So again, this is all of a huge application these days, right? Maybe you might have come across something called a broadband, right? And how information goes through a broadband. This is all because of total internal reflections. Alright, so I said, here I have, this is the structures of optical fiber. Alright, so optical fiber consists of a two transparent layer. This is what we call as a glass core and glass plating, right? The refractive index of a glass core is higher than refractive index of a glass plating, right? So, and this is the plastic cover, and what happens is, I'm going to send a light or informations, alright, electromagnetic wave or light with some suitable angle of incidence. This is the information I'm going to send, and I'm going to send a light such that incident light should be more than critical angle. If an angle of incident is more than a critical angle, this is grating. Refractive index is this. Let's say this is N1, this is N2. N2 is more than N1. You see light going from denser to rarer, right? So if angle of incidence is more than critical angles, instead of light passing through a next transparent medium, it undergo reflections. Alright, so it undergo reflections, it undergo repeated. Alright, so there is total internal reflection taking place in a core. Alright, so therefore I say electrical signals can be converted into a light, and such a signals or such a light sent through optical fiber, and then finally you get informations, and this information can be converted into electrical signals, and then you can see it through a monitor or through computer or whatever, right? So this is how light travels. Alright, this is again, I have a diagram. This is optical fiber, this is a plating, this is a core. Refractive index is less here, total internal reflection take place. So now the point is, what is the advantage of this optical fibers? Advantage is that total internal reflections. There is a minimum loss of signal. Alright? Since there is a minimum loss of signals, alright, you can make a signal to travel much longer distance without losing much intensity. So this is the huge application of optical fiber. So therefore I say that transmitting and receiving electrical signals which are converted to a light, Why? Because light has to pass, right? Light means electromagnetic wave. Light doesn't mean that it is in the form of visible light. It could be of any wavelength, right? And then since there is a minimum loss of signals, right? Therefore, it is preferred, right? And we prefer such a optical fiber. We prefer it to travel much longer distance, right? So therefore, optical fibers are extremely used for transmitting audio and video signals to a long distance, right? So this is one very important applications and which we use these days. And we are done with total internal reflection.